This is the second roller coaster video that I'm doing. The first one pretty much went through how to solve this type of question. I'm hoping to get absolutely maybe 3 done. 3 roller coaster questions. This one, the focus is going to be on how to solve it when the cart up here starts off with some velocity. So I'm going to start this cart off with 20 meters, that might be a bit rough for the passengers, 10 meters per second of horizontal speed. This gives it some starting kinetic energy. Now, since it starts with some kinetic energy, and then it also gains kinetic energy as it loses gravitational potential energy, so there's a transfer from UG to EK, it'll gain speed. And we're going to look at how to solve for how much speed it's gaining as it goes down. And as in the last question, we're going to look at the points D, C, A and B, and we're going to solve for either some or several of these variables: the speed, the centripetal acceleration, the net centripetal force, and then the normal force. And the one detail I will add is that I've decided at C we do solve for the normal this time, but with the added bit of information that at C the tangent there is 45 degrees. The track is sloped at 45 degrees at C. Let's start at D first. We can't solve for any of the circular values, so these are out, but we can solve for the normal force at D. At D, the object is pretty much travelling horizontally to the right. It's not travelling up or down. Therefore, all vertical forces have to cancel out. There's the weight force. Here is the normal force. If they cancel out exactly, the normal force predictably is 2,000 newtons. 2,000 newtons. So normal at D is equal to 2,000. Let's now find the speed at C. How much height has it lost? It's gone down from 45 meters to 15 meters. So the change in gravitational potential, mg delta h, that's 200 times 10 times negative 30, which comes to, what's that, 60,000? Negative 60,000. So it's lost 60,000 joules of gravitational potential energy. Since this is a no-friction roller coaster, it's gained 60,000 joules of kinetic energy. So that's equal to the change in kinetic energy. Up until this point, this question is very much like the question we did in video 1 on roller coasters, but in this case, the change in kinetic energy is not equal to the final kinetic energy. That's only the case when you start out with speed 0. So if you start out at height 0 and your change in height is 10, the final height is also 10. If you start out at height 5 and your change in height is 10, you end up at height 15. Since we've started out with some kinetic energy and we know the change in kinetic energy, we have to find the final kinetic energy by adding on to the initial kinetic energy the change, like so. What is the initial kinetic energy? EKI is equal to a half mv squared. That's a half times 200 times 10 squared, 10,000 joules. So EKF is equal to 10,000 joules. That's the amount it started off with in terms of kinetic, plus the 60,000 joules worth of kinetic energy it gained. So the kinetic energy at C is actually 70,000 joules, not 60,000 joules. If the kinetic energy at C is 70,000, that must be equal to a half m speed squared. So I'm going to multiply 70,000 by 2, divide it by 200, and then take the square root of that entire sum, and I get 10 times the square root of 7, or 26.46 meters per second, and that is the speed 46 at C. What is the normal force at C? Well, if we draw the part of the roller coaster, at C out over here, we have a line down there, we have the cart on the line there, we have the weight force here, that's 2,000 newtons. Since there's no friction, the normal force acts at right angles there to the surface, and we can also separate that normal force into 2 components. The vertical component Wait, no. What we can say is that... Oh, no, that's a bit different, isn't it? I've decided I don't want to do that. I want to separate the gravitational force into two separate components. One force acting parallel to the slope, down like that, and one force acting perpendicular to the slope. If this angle here is 45 degrees, that angle in there is 45 degrees. That's just something you're going to have to remember. Since the kart is not moving either off the track or sinking into the track, the forces perpendicular to the plane of the track have to balance. This is all covered in videos previously. That means this section, this component of the gravity force here, has to equal the normal force up here. And this component of the gravity force is given by cos 45 degrees 2000, which is 2000 times 1 on root 2, which comes to 1414. So this particular component of the gravity force is 1414. And again, as I say, since the kart is neither flying off the track or sinking into it, that balances out perfectly with the normal force. The normal force at C is equal to 1414. So normal force, to complete this diagram, 1414. And then it's this component of the gravity force acting in this direction which actually is accelerating that kart down the slope. If that has just confused you, go watch our videos on masses on slopes. Okay. Again, we can't solve for any of these values at C because the object at that point is not moving in a circle. But at A, it does begin to move in a circle. So I'm going to delete all this and just leave the fact that the initial kinetic energy, the initial kinetic energy was 10,000 joules. That'll be important later on. So at A, we're going to figure out the speed, the centripetal acceleration, the net centripetal force, and the normal force. First of all, we need to know the speed. How much kinetic energy has the object gained since it dropped down that much? Well, that must equal the loss in gravitational potential energy. So delta UG is mg delta h. By the time it gets to A, it's lost 45 meters of height. So that's 200 times 10 times negative 45. Oh, I knew this when we did the last question. Let's figure it out again. 2,000 times negative 45. Negative 90,000 joules. That must mean it has gained 90,000 joules of kinetic energy, and its final kinetic energy at A is going to equal 90,000, which is the change, plus the initial 90,000 plus 10,000, 100,000 joules. That must also be equal to a half mv squared. So that's 200,000 divided by 200. Take the square root. I get 31.6. V is equal to 31.6 meters per second. Now notice, if it had just 90,000 joules of kinetic energy, its speed at A would be 30 meters a second. That's what happened in the last video. In the last video, it had 90,000 joules worth of kinetic energy at A because it started with 0. Now notice, we started at this time at 10 meters per second, but when it reached the bottom point, it was only going 1.6 meters a second faster. And that shows that even if you put in a lot of speed at the start, an object at great speed, you really lose the advantage as you let it fall under the force of gravity. And that's to do with the fact that energy scales by the square. It's not linear in terms of velocity. Anyway, moving on to these values over here. We have VA is equal to 31.6. AC is equal to V squared on R. We know R is 10 meters because the difference in height between A and B is 20, so R is half of that. So you've got V squared on R, that's 1,000, no, that's 31.6 squared, which is around 1,000, divided by 10, that is 100, AC, so centripetal acceleration at A is equal to 100 meters per second squared. the net force centripetally at A is equal to the mass multiplied by this. That's 200 times 100, 20,000 newtons. And now the normal force, let's draw the section of track because people are always mucking this part up. Here's the section of track we're looking at. Here is the roller coaster cart, mass 200. We know it has net force. How much? It'll be 20,000 newtons in that direction there. What are the forces actually acting on this cart? Well, we've got gravity force down there, 2,000 newtons. And then we've got the normal force. If we want the gravity force to add up with the normal force to equal this net force, which direction does the normal force have to act in? Of course, has to act in that direction there. And it's quite large. We have to have a normal force that's big, which then gets taken away by the gravity for a second. No, sorry, not for a second, just a little bit, to give us that net force there. So we know that the normal force, take away the gravity force, is equal to the net force. N is equal to 22,000. Never put a plus there when you're figuring out the cart at the bottom of the roller coaster. You put a plus here when you're figuring it out at the top. So, deleting this working up here. Well, I think I've saved everything. Don't need V. Don't need this. Don't need this. Don't need that. And I'll delete this section of track here. Okay, so the normal force was equal to 22,000 newtons. That's all at A, by the way. We'll move this down here. Now let's figure it out at B. If it had 100,000 joules of kinetic energy at A, and then it climbs that 20 meters, the change in gravitational potential is mgh, which is 200 times 10 times 20, which is equal to 40,000 joules. That gravitational potential energy must have come from the kinetic energy, since total energy has to be conserved. So negative 40,000 equals the change in kinetic energy. That means the kinetic energy at B equals the kinetic energy at A, take away 40,000. So that's 100,000, take away 40,000, 60,000 joules. And that must also be equal to a half mv squared, so 60,000 times 2 divided by 200, take the square root, that comes to 24.5. 24.5. Let's check this for a second. I do believe it starts out, that's just very similar. No, last time we had 24.45. So this time it is 24.5. V is equal to 24.5. I'm thinking of the last lesson we did. I thought I was getting the same speed. No, in the last lesson the speed was 24.45. So the speed at V, and that was over here. Yeah, very different. The speed at B is equal to 24.5 meters per second. VB. The centripetal acceleration at B is equal to V squared on R. So that's 24.5 squared, which is 600 divided by R, which is 10. 60 meters per second squared. The net centripetal force at B is the mass times that, so 200 times 60, 12,000 newtons. And then the normal force, well, we draw the section of track we're interested in. There it is. We draw our cart, 200. We draw our net force. There it is there, 12,000. We draw our gravity force, 2,000. And then we ask ourselves, which direction does the normal force have to act in order to make up that net force from the force we have already? Now, if we have the normal force acting that way, there's no way we'll ever make up that red net force there. we need another arrow acting the downwards direction, so we can add this to this and get this arrow here. So we have normal force plus gravity force is equal to 12,000, or the normal force is equal to 12,000 take away 2,000, which comes to 10,000 newtons, or around 5G for the people feeling that on their bums on the roller coaster. And that is pretty much all we have to work out for this question. The only thing you should realize is that if it starts with some velocity, that means it starts with some kinetic energy, and you have to carry that kinetic energy all the way through the question when you're working with gravitational potential, kinetic energy exchanges. Now I want to do one more question on roller coasters, and this question will be a work backwards question. So instead of giving the starting velocity, I'll give the normal force at a particular point, and we'll work backwards to solve the rest of the